Many CAN bus faults can be diagnosed by connecting an oscilloscope to the bus wires and observing the waveforms and messages that are flying across the network. However, certain faults, such as intermittent wiring faults and loss of one of terminating resistors, are harder to spot. Also, sometimes it's necessary to perform diagnosis on a powered-off CAN bus. Standard approach in such situation is to put an ohmmeter across the CAN high and CAN low bus wires and observe the resistance. As each terminating resistor is around 120 ohm, the diagnostician should observe around 60 ohm resistance for a properly wired CAN bus system. However, many ohmmeters are too slow to catch intermittent events. This video proposes a way to use an oscilloscope to test a powered-off CAN bus system. To do this, we need to add two things. Firstly, we need to take a voltage source, for example 1 volt, and connect it to CAN high using a 600 ohm resistor. For example, for that we can use a Pico AWG. The second thing is to connect a 470 ohm resistor from the CAN low to the ground. This way we are creating a voltage divider, so the voltage on channel A should be around 470 millivolts, while on channel B it should be around 420 millivolts. Also, we can notice is that if we divide A by B, subtract 1, and multiply by the value of the grounding resistor, 470, we'll get 60 again. So we can use this formula to calculate the resistance value that we should observe for our terminating resistors. If we notice that these voltages jump around or they change values when we wiggle some connectors, it will mean that there is a wiring fault in the system. And we can catch it by using masks and alarms in the PicoScope software. This test will allow to easily notice faults like short from CAN low, CAN high to ground, short between the CAN lines, or loss of terminating resistors. However, if you suspect that either CAN high or CAN low are shorted to another wire that is unpowered, so it doesn't carry any voltage at this point, we need to make sure that such a wire is grounded. So that would be a proper test for such wire. Alright, without further ado, let's proceed to a bench test of this approach.
Okay, here is the setup. I have an unpowered CAN bus driver that is connected to this small PCB that has a terminating resistor between the CAN high and CAN low, and then those wires snake around and go for a few meters until they return back to this breadboard, which has another terminating resistor, and there is a channel A and channel B of PicoScope connected across it. There is also a 470 ohm resistor connecting a CAN low to the ground, and finally there is a AWG supplying 1 volt to CAN high. Now let's power up the PicoScope and see what happens on the screen. Okay, so the PicoScope is running and I'm using plus minus 1 volt for each channel. The time base is 200 milliseconds per division, which means I'm collecting 2 seconds across the screen, and the PicoScope is in the streaming mode. I'm collecting 100 kilosamples for each screen, which means that the sample rate is 50 kilosamples per second. I'm also using 10-bit resolution enhancement on each channel so that I filter out some noise, and my AWG is producing a DC voltage 1 volt, and we see constant voltages on channel A and channel B, 460 millivolts and 420 10 millivolts respectively. We could go ahead and set up masks for both channels, but to make our life easier, we can do some math and enable a math channel that will show us the value of the terminating resistors directly. So we can go to math channels and define R_can math channel, which is the following. So it's 470. Remember that's the resistor value that connects CAN low to ground, multiplied by A divided by B minus 1, and that should give us the value of the terminating resistors. So this value is measured in ohms, and I have a range defined from 0 to 500. I click next, it's all set up. Let's try to enable it. So we are done here. It's showing us the trace, which is approximately 60 ohms, just as we wanted. So our CAN bus physically is intact, and we have two terminating resistors that are giving us a 60 ohm value. Perfect. Now we are ready to add a mask to this channel. So let's go to Tools, Masks, Add Masks. Select channel R_can and click Generate. So it suggests to generate a mask with a 25 ohm window, but we can do better than that and have a 10 ohm window. So we click Generate and we are done. We click OK, and there should be a window mask appearing around the channel. If we now run the Pico scope, it's going to collect the trace, and if everything is normal with our CAN bus, the trace should be fully within the mask window, and it's not going to trigger any events. And speaking of which, we need to make sure that we can properly register the events. So let's go to Alarms and click on Beep and make sure that the event happens when the masks fail. And so here everything is set up. So once the signal is outside of the mask window, the Pico scope is going to produce a beep, and we will hear it, and we'll see on the mask where exactly the failure happened. I'm now going to start the capture and introduce the following faults. First, CAN low to short to ground, CAN high short to ground, then CAN lines shorted together, and finally one of the terminating resistors is going to have an open. Okay, let's go. CAN low to ground, CAN high to ground, CAN lines shorted, terminating resistor open. We are done with the test. Now we stop the Pico scope and examine what happens on the screen. Obviously we had some events, and we can see on the mask in white what exactly they were. So at some point the value dropped down to almost 0, at some point it went double, and sometimes it just goes all over the place. So now we can go back on our screens and see what exactly happened. Okay, starting from screen number 1, there is nothing abnormal happening for a few screens, but then we get this guy. So our value for resistance goes through the roof. and that corresponds to channel A dropping down considerably, but not all the way to 0. Channel B is the one that goes all the way to 0, which corresponds to CAN low being shorted to ground. Next, we see on screen number 7, unfortunately almost dropping through the cracks here, but we can still see here that channel A is dropping all the way to 0 and channel B doing exactly the same. So this corresponds to CAN high being shorted to ground. Okay, so on screen number 9 we see that the resistance value drops almost all the way to 0, which corresponds to CAN lines being shorted together. Very nice capture. Not that much difference on channel A or B, but resistance values we can see change loud and clear. And last but not least, on screen 11 we see that our resistance value suddenly got doubled, and that corresponds to one of the terminating resistors developing an open, and we see that the value goes from 60 to 120 ohms. So this is the end of the test. We were able to confirm how we see some of the faults in the CAN bus, and hopefully this will be useful for real-world diagnosis.